Hello everyone, I'm Suhong from UC Berkeley. I'm going to introduce our work on embedding dynamic approach to self-supervised learning. This is the joint work with Domas Buracas, Dr. Seunghyun Park, Professor Jinkyu Kim, and Professor John Canny. Our work is motivated by the following problems. First, contrastive methods often require a careful treatment of negative pairs, which need a large memory overhead. Next, non-contrastive self-supervised learning method is prone to mode collapse problems since it does not have any explicitly perceived force to disperse embeddings. For example, the implicit effect of the batch normalization layer is known to help BYOL method to circumvent the mode collapse problems. And the model with other normalization layers, such as layer normalization or instance normalization, fails to learn express representations for BYOL. And therefore, the mechanism that non-contrastive self-supervised method don't suffer from the mode collapse is somewhat enigmatic. So we hypothesize that the batch normalization layer reveals that there is a strong stochastic component in gradients beyond the global normalizing component, which depends on the activations of the images and their batch centroids. This force provides a local dispersive force between embeddings. However, it is a suboptimal way to achieving the two desirable features of a good representation, that is local and global dispersion of embeddings. For this reason, we propose a method that moves the dispersion from the network layers to the loss layers. This allows network normalization layers to be independently designed while separately defining and optimizing the local and global dispersion losses. Hence, we explore multi-view, singular value, and Brownian diffusive losses. Let me introduce multi-view centroid loss first. As opposed to BYOL, we train the online network to predict the target network's centroid representation of differently augmented multiviews of the same image. We generate k differently augmented views of input image X. Given k outputs from the target network, we use the center of these k outputs as the centroid representation. Lastly, we compute the sum of L2 losses between the target network's centroid representation of embeddings of k different views and the online network's representation. This loss applies an attractive force to pull together multiple augmented representations of the same image into the geometric centroid as the pivot to cluster embeddings. Then we bring singular value loss as a dispersive force that encourages uniformity of the embedding distribution. Singular value loss exerts the force to regularize the shape of embedding distribution to be globally spherical at large scale. We use a dispersive loss called Brownian diffusion loss that induces a Brownian motion of the online network's representation. Brownian diffusion loss addresses local dispersion in the embedding space. The diffusive force for k-augmented embeddings is exerted in the same direction. This is the linear probing result on ImageNet. Our method, trained only for 300 epochs, achieved performance matching swap with multicloud, which is trained for 400 epochs. Thank you for listening to my presentation.